let's do a pretty straightforward example of interference considering phase or path difference. So let's say you're standing in between two speakers, and there's a couple of distances here. The speakers are separated by 10 meters, and you're 1.5 meters from the speaker on the right. The two speakers are playing a tone of 49 hertz, and let's say that the speakers are playing sound in phase. Okay, so I didn't write that down here, so I'm going to put that there in brackets. In phase. So our first question is, what is the wavelength of the sound? So if we want to find the wavelength, we'll remember our equation that V equals F times lambda. So part A, what is the wavelength? V equals F times lambda. We know F is 49 hertz. We're going to assume we're standing in air at 20 degrees Celsius, so V is 343 meters per second. So lambda, the wavelength of the sound, is V over F, 343 meters per second, divided by 49 hertz, which is seconds to the -1. We get a wavelength of 7 meters. So the wavelength of the sound coming out of the speakers is 7 meters. Part B, what is the path difference where you are standing? So here's where you have to remember what path difference means. Let's label our speakers number 1 and number 2. I'm going to call the one on the right number 1, and I'm only picking that one as number 1 because it's smaller, because it's closer. I'm going to call the one on the left number 2. X1 means the distance between you and speaker 1. X2 means the difference between you and speaker 2. And delta X is the difference between those two numbers. So let's see what those guys are. X1 we see from the picture, 1.50 meters. X2, we don't see it exactly in the picture, but we kind of see it. This is 10 meters from here to here. It's 1.5 from here to here. So this must be 10 take away 1.5. So that would be 8.5 meters. Okay, now we're ready to do part B. What is the path difference? Delta X is the difference between the two paths. So X2 take away X1. So X2 is 8.5 meters. We subtract X1, which is 1 meter. 8.5 subtract 1.5 gives us 7. So our path difference is 7 meters. So there's the path difference where you are standing. If you moved around, if you were at a different location, there would be a different path difference. Okay, part C, what is the phase difference? Let's use our equation that relates phase difference and path difference. And that equation says that the phase difference delta pi is 2 pi times delta x divided by lambda plus delta phi naught. Delta phi naught is the difference in phase constant between the two sources. They're playing their sound in phase, so delta phi naught is equal to 0. So what we have then is 2 pi times 7 meters divided by the wavelength, which is 7 meters, plus 0 equals 2 pi. Then the question asks, do you hear a loud sound or a quiet sound? It's important to be able to relate this to constructive and destructive. A loud sound would be where two sound waves come together and get bigger, so loud would be constructive. What we know about constructive is that delta phi equals 0, 2 pi, 4 pi, and so on. If it's quiet, then the two sound waves come together and we don't hear anything, so they must cancel each other out. They must be destructive. When that happens, the phase difference is an odd multiple of pi. So it's pi, 3 pi, 5 pi, and so on. So let's look what we found here in part C. For part C, we see that delta phi, the phase difference, is equal to 2 pi, which is our condition for constructive interference, so we must hear loud sound. So for part D, we see that delta phi equals 2 pi. That's constructive interference. And if it's constructive interference, it must be loud sound. Okay, that one's pretty straightforward. We will get more complicated, but it is always good to start at the beginning.